Vsepr, Vsepr, valence shell electron pair repulsion. This is a method, a theory, that we are going to use to help us predict the shape of molecules using their Lewis structures, using how many bonds and how many lone pairs are on the central atom in a molecule. We can predict with stunning accuracy, actually, the shape of simple molecules anyway. And we can extrapolate that somewhat to larger ones as well, but we're only going to look at simple ones here in this class. The basic theory, the basic idea behind Vsepr, behind the Vsepr, is the idea, and it's not really an idea, it's the fact, that electrons don't really like each other. Electrons have similar charges, like charges repel, and so groups of electrons on an atom will get as far away from each other as possible. They have 3D space to work with. They have, 360 degrees all the way around the atom to work with, and they will position themselves as far away from each other as possible, because that is the most energetically stable way for them to arrange themselves. Because again, they repel each other. Groups of electrons don't like to be bunched up next to each other. It's kind of like, people right now. They don't want to be up close to one another. They're going to get as far away from each other as they can. So, when we're looking at our molecules here, we are going to be largely concerned with the central atom, especially for our purposes here in this class. Like I said, we could take this to more complicated molecules where there's not just a central atom and then stuff attached to it, and it would still work going to more complicated molecules, but we're going to look at just molecules where there's a central atom and then things attached to it. That's all we're going to concern ourselves with. So what we're looking at here is how many atoms are bonded to the central atom and how many lone pairs are on the central atom. Now notice here we are talking about the number of atoms that are bonded to it, not the number of bonds. I think I'm going to run out of space there. Yep, run out of space. So not the number of bonds. We're not talking about the number of bonds, because if we have a double bond, that is still just one atom attached to the central atom. We are going to count double bonds and triple bonds as one group. I'm going to be as careful as I can to always talk about groups of atoms, not bonds, because a single, double, and triple bond in Vsepr are all treated the same. We're only concerned with how many things are attached to the central atom. So how many atoms are bonded to it, regardless of how, just how many atoms are bonded to it, and then how many lone pairs are attached to the central atom. Alright, and if we have something like if one of these was chlorine instead of hydrogen there, and so the chlorine had its own 3 lone pairs, couldn't care less. We do not care about those lone pairs. Only lone pairs on the central atom, not the rest. Alright, when we're drawing these, which you will have a homework set to practice over this with, we're going to be using dashes and wedges to do that. So normal lines like these are meant to represent bonds that are in the plane of the paper, or the screen in this case. So these bonds are actually in this plane right there. When you have a wedge like this, that is meant to show that that bond is coming out of the screen towards you. So in 3D space, it is oriented towards you. Not necessarily directly out. It's not at 90 degrees to the screen, but it is somewhere oriented out towards you. And then the dashes, which I will often actually write like this instead. I think it looks a little bit better. Some students just state it looks like a Wi-Fi signal, but I think it looks better to have it kind of similar to the wedge, where you can see the directionality but just normal dashes is fine too. It's just I prefer it this way. And so this represents going back away from you. So it would be behind the plane of the screen. And I will do my best to draw examples for you as we go along. So when we're classifying something using Vsepr, we're going to use this classification system here, and it is based simply on what we just talked about a second ago. A in this classification system represents the central atom, and so it is always going to be there. We're not going to change it at any point. It is always just going to start with A by itself. B sub x is the number of things bonded to it. These are often called ligands, by the way. It's just the sciencey term for the atoms attached to the central atom. So this is just the number of things attached to that central atom, and the number will take the place of that x. So if there are 2 things attached to it, it would be A, B, 2. So it's saying 2 different things bonded to the central atom. Again, not 2 bonds. It could be 2 bonds, maybe, if both of the bonds were single bonds, but that's not what it's telling us. It's telling us there are 2 things bonded to the central atom. And then E represents the number of lone pairs. So if we had 2 lone pairs, then it would be E2. And so then the whole thing would be A, B2, E2. 2 things bonded, 2 lone pairs on the central atom. And these numbers, the number of lone pairs and the number of things bonded, directly relate to the shape of the molecule. So let's look at some examples here. So if we have 2 groups of electrons around our central atom, there's only one shape that can give us, and that is a linear shape. And so, for example, here, if we had CO2, notice here we don't care that there are actually 4 bonds, because both of them are double bonds. They're going to end up still giving us that linear structure, because we only care about the number of things attached, not the number of bonds. And so that is a linear molecule. What if we have 3 things attached to the central atom? If we have 3 things and all of them are bonds, we might have something like boron trifluoride. And I am drawing the 3D structure here. So boron trifluoride is going to have what we call a trigonal planar structure. This is when being in class and having a model to show you would work really well, but I'm going to have to do the best with what we have. I would encourage you to go to your book, and they have some images of 3D shapes there that will hopefully help you be able to visualize the actual shapes that we're going to be seeing here. But boron trifluoride is 3 things bonded to the central atom, and they're all 120 degrees apart, and they're all in the same plane together, and so that's where it gets the name trigonal planar. And by the way, this is the molecular geometry. The molecular geometry is only taking into account the atoms bonded to the central atom. We'll also be talking about the electron geometry. The electron geometry is taking into account everything that is attached to the central atom. So molecular geometries would not take into account lone pairs, essentially, but electron geometries do. And the electron geometry will always match whatever the name is for the geometry that has only things bonded to it. So down here for the next one, for example, so AB2E1, if we have 3 things attached to the central atom, 2 of them are bonds, and 1 of them is a lone pair. Sulfur dioxide is an example of that. It has 2 bonding groups and 1 lone pair. The molecular geometry ignores this lone pair. And if you ignore the lone pair, it just looks like someone took a linear molecule and bent it. And so this is called a bent molecular geometry, but the electron geometry is still trigonal planar, because you still have three things 120 degrees apart. It's just for the molecular geometries we ignore the lone pairs. All right, so that is bent. If we move up to 4 electron domains, and all the things attached to the central atom are bonds, we get a tetrahedral molecular geometry and electron geometry, and methane is an example of that, which we actually saw just a minute ago on the previous slide. Tetrahedral geometries are the first ones to actually go into the third dimension. So we no longer have everything in a plane together. These are all 109.5 degrees apart. And the actual tetrahedral shape, in my mind, is almost like a visual illusion, because depending on how you hold the model, it can really look like one position is different than the rest, but they're actually not. They're all identical. There's no difference between this hydrogen and that hydrogen and this hydrogen. They're all exactly the same. If we replace one of those bonds with a lone pair, we would still have tetrahedral electron geometries, but the molecular geometry would now be Trigonal Pyramidal. And this is something that ammonia has. Ammonia has this geometry. And so again, the electrons are still arranged the same way, but and it's really, I can't really draw it where you could see it, but if you could see the model here, the three bonds make a triangle that would be like the base of a pyramid, because they all go up towards the nitrogen. So we would get the name Trigonal Pyramidal is the name of this molecular geometry. If we take another one of those and replace it with a lone pair, we would get what the structure of water is. And actually, a better way to draw this, let me draw that slightly differently. That's not a terrible way to draw it, but I think it's a little bit easier if I put the lone pairs here. So the lone pairs are in the plane of the board, and those are going towards you and back away. And so this is what we call bent. Because again, if we ignore the lone pairs, it once again looks like you took a linear molecule and just bent it. So it has tetrahedral electron geometry and bent molecular geometry. Things get a little bit spicier when we get to 5 electron domains, because when we have 5 things attached to that central atom, we can no longer find a geometry where all 5 of the positions are the same. Up to this point, whether we had 2 things, 3 things, or 4 things, all the places you put stuff are exactly the same. There's no difference from one to the other. But when you have 5 positions, it's not possible to do that. And so what we're going to have instead is something like this. This is a phosphorus pentachloride. And this is going to have, oops, sorry, not fluorine, chlorine. You have radial positions, and, well, planar positions and axial positions, actually, I think is the proper terminology. So hopefully it's at least partially clear, the shape that I'm drawing there. So we have 3 atoms in a line here that are in the plane together, and those are the axial positions. So these 2 positions here are actually different from these 3 positions. So these 2 positions are 180 degrees apart. These 3 positions are 120 degrees away from each other and 90 degrees away from the axial positions. And so because not all those angles are the same, we have essentially 2 different groups of locations, 2 different places we can put them. We can put stuff in the axial positions or in the planar positions in the middle. So this is Trigonal Bi-Pyramidal, because it's like you took two three-sided pyramids and put them base to base on each other. If we take one of these out and replace it with a lone pair, like for example with sulfur tetrafluoride, it matters where we put the lone pair. We need to put that lone pair, sorry, I'm running out of room there. We need to put the lone pair in one of these planar positions, because the lone pair is actually a little bit bigger than the bonding groups. It takes up a little bit more space, and so the lone pair would rather have two 90-degree interactions here and two 120-degree interactions. That is preferable to having three 90-degree interactions, which is what it would have if it was at one of the axial positions. It would be at 90 degrees to all three of the things on the plane, and then one 180-degree interaction. So it's better for it to have just the two 90-degree interactions. And again, you can't really see it from the way I've drawn there, but if you were to take a model of this and put it in your hand, you can push the model back and forth on the two positions here like a seesaw. It actually does kind of rock back and forth like a seesaw. And so this has the molecular geometry of seesaw, the funniest name of all the ones we're going to see. But again, it still has a trigonal bipyramidal electron geometry. If we replace another bonding group with a lone pair, that lone pair still needs to go onto the planar positions. And so in bromine trifluoride, write it over here, we are now going to have, actually, hold on, that's not the right way to start that. So let's see, I need two on the plane. Why did I do that? So I'll have one here, and I'll put one here, and then I'll have the three fluorines like this. And actually, I'm not going to put the lone pairs in on those fluorines, but they do have their full lone pairs. This position, or this molecular geometry, is called T-shaped, because if you ignore those lone pairs, you have 90-degree interaction here between each of those, and then it's 180 degrees here, and so it is actually just shaped like a T. And then the last one here, if you have a third lone pair, you're going to take up that last position on the plane, and so Xenon Difluoride is an example of that. And so all three of these planar positions are lone pairs, and you have two fluorines on the axes. And so this is, if you ignore the lone pairs, it looks just like a linear molecule we saw at the beginning. And so it has the molecular geometry linear. But again, still has the electron geometry of trigonal bipyramidal. So the last group here, if you have 6 things attached to your central atom, you have what's called an octahedral molecular shape. So sulfur hexafluoride is an example of this. And with octahedral shapes, everything is 180 degrees or 90 degrees away from everything else. So each one of these positions is 90 degrees from every other position except for the one that is directly opposite to it, and that's 180 degrees. And so if you actually, the reason it's called octahedral, by the way, is if you put planes between all of the different atoms, you would have an 8-sided shape. So that is why it's called octahedral. If you replace one of those with a lone pair. It doesn't matter which one you replace. They're all the same. You would get square pyramidal, and so bromine pentafluoride is an example of that. And I'll just put the lone pair on the bottom here, just for the simplicity's sake. And again, I'm not going to write in the lone pairs on the fluorines. But hopefully you can kind of see there how that makes a four-sided pyramid if you're ignoring the lone pair there on the bottom. So that's where we get square pyramidal. Still has octahedral electron geometry though. And then the last one is square planar. And it does matter where you put this second lone pair. Because again, the lone pairs, being a little bit bigger than the bonding groups, don't like to be next to each other. So they will be on opposite sides of the central atom. So Xenon Tetrafluoride is an example of this. So we would have xenon in the middle. The lone pairs would be on opposite sides. And then you would have 4 bonds all in a plane together with the xenon. And so we get square planar from that. All right. I think, and by the way, these are all the examples that I just showed you here. And so this nice little figure here, or a table, will be really handy for you when you're trying to go through and identify Vsepr shapes, because it has all of the numbers, the total number of groups, the number of bonding groups, number of lone pairs, and then the electron and molecular geometries that you get as a result of that. So I think we'll call it there for this one. In the next one, we will identify some Vsepr shapes of different molecules.